James Webb Telescope is about to make huge discoveries. It took years to build something as amazing as the famous James Webb Telescope. But what took so long? The telescope's basic design hasn't changed much over the years. But you know what has? The science that Webb can dig into. Back when scientists first imagined this telescope, they hadn't yet discovered dark energy. Astronomers also hadn't yet discovered exoplanets, planets orbiting other stars. Those recent advances have raised big questions about the universe, and the James Webb Space Telescope could be a great tool to help answer them. Welcome to Space World. In today's video, we are going to talk about how James Webb is going to make huge discoveries in the cosmos. So if you want to know more about it, then stay with us until the end of the video. Webb has a unique design, as Webb's big mirror and shield are an awkward shape to fit on a rocket. So Webb launch folded up, and the massive machine unfurled itself in space. But Webb's strange design was always part of the plan. The telescope was first dreamed up in 1989 as a successor to the Hubble Space Telescope, which was about to launch. Astronomers wanted the newer telescope to see light at infrared wavelengths. That would complement Hubble's ability to see ultraviolet, visible, and near-infrared light. Scientists also wanted the telescope after Hubble to have an even bigger mirror, as the bigger mirror would be able to collect more light, and the more light a telescope can collect, the farther it can see into space. In addition, the project was delayed several times because building and testing the spacecraft took so long. Other slowdowns were because of human errors. For instance, someone used the wrong cleaning solvent on the telescope. This mistake damaged valves in the propulsion system. More recently, shutdowns due to the coronavirus pandemic also pushed the launch back. I don't think we ever imagined it would be this long, says Friedman. But there's one silver lining. Science marched on. So, one of Webb's original goals was to study galaxies like our own Milky Way. That is still the dream, partly because it's such an ambitious goal. To achieve this, Webb will peek at galaxies and stars as they were just 400 million years after the Big Bang. At that time, the universe was about 3% of its current age. This is when astronomers think the universe became transparent to light. Before that, all matter existed in a soup of charged particles. Light struggled to get very far through that particle soup. Webb can see so far back in time because it observes infrared light. These wavelengths are too long for the human eye to see. But these are wavelengths where a telescope can see the earliest objects in the universe. Here's why. Light travels at a fixed speed, so it takes time for light from any distant objects to reach us. Looking at very far-off objects means we're seeing them as they were long ago. Since the universe is expanding, light from those early distant objects gets stretched out before reaching our telescopes. For the farthest, earliest objects out there, that light gets stretched out to infrared wavelengths. In the 1990s, astronomers wanted to look at the early universe to solve a problem. Back then, the universe was thought to be 8 billion or 9 billion years old. But some stars seemed to be about 14 billion years old. In 1998, cosmologists solved that mystery. It turned out the universe was expanding faster and faster. If that was true, then the universe must be older than astronomers thought. The current age estimate is about 13.8 billion years old. Scientists call the mysterious substance that drives the universe's accelerating expansion dark energy. Furthermore, the rate of expansion for the universe is known as the Hubble constant. For several years, different methods for measuring it have given different answers. Friedman calls the issue the most important problem in cosmology. The question is whether the mismatch is real. That is, does how fast the universe expands really look different depending on how you measure it? If so, that could indicate something profound about the nature of dark energy. But the differences between measurements might just be due to errors. Webb can help settle that debate. One way to measure the Hubble constant is to measure the distance of speeds of far-off objects whose brightness is known. If you know its actual brightness, you can calculate the object's distance based on how bright it looks from Earth. Objects of known brightness are called standard candles. Exploding stars or supernovas are standard candles. So are special stars that give off pulses of light. These stars are called Cepheid variables. Studies using those standard candles have found one expansion rate for the universe. That rate is 74 kilometers per second for every 3 million light-years of space. But red giant stars are also standard candles. Studies using them have gotten a smaller expansion rate. That rate is only 69.8 kilometers per second per 3 million light-years. Another way to measure the Hubble constant is to look at the cosmic microwave background. This dim glow of light was emitted just 380,000 years after the Big Bang. Calculations based on that glow give an even smaller expansion rate. They measure just 67.4 kilometers per second per 3 million light-years. These numbers may seem close, but the fact that they disagree at all is a big deal. It could change our understanding of what the universe contains and how it evolves over time. For scientists, this mismatch is a crisis. So in its first year, Webb will observe several standard candles. It will look at Cepheid variable stars and red giants. It will also observe strange stars called carbon stars. Perhaps the biggest change in astronomy during Webb's development has been the rise of exoplanet science. When Webb was proposed, exoplanets were scarcely a thing, says Friedman. Now, of course, it's one of the hottest topics in all of science. One of Webb's original goals was to detect Earth-like planets around other stars. There, it could search for evidence of life. But 25 years ago, only a handful of planets orbiting other sun-like stars were known, and all of those worlds were scorching hot gas giants. They looked nothing like Earth at all. Since then, thousands of exoplanets have been found orbiting distant stars. Scientists now think that there is at least one planet for every star in the sky. Some of those planets are small and rocky, with the right temperature for liquid water. That makes them promising spots to look for life. Most of these exoplanets were discovered as they crossed or transited in front of their parent stars. As a planet does this, it blocks a little bit of the star's light. This reveals its presence to astronomers. What's more, if that planet has an atmosphere, the starlight behind it filters through that gas. By peering at that filtered starlight, a sensitive telescope can tease out the gases in the atmosphere. 2 space telescopes have already started this work. One is Hubble. The other is the Spitzer Space Telescope. Like Webb, Spitzer observes infrared light, but Spitzer ran out of coolant in 2009. As a result, the telescope is too warm to measure important molecules in exoplanet atmospheres. Hubble, meanwhile, is not sensitive to some of the most interesting wavelengths of light. These are the wavelengths that could reveal alien life. When it comes to observing exoplanets, using Hubble is like peeking through a crack in a door. But Webb will throw that door wide open, says Nicole Lewis. She studies exoplanets at Cornell University in Ithaca, New York. Unlike Hubble, Webb is sensitive to several molecules that contain carbon. Such molecules in an exoplanet atmosphere could be signs of life. And this is it for today, guys. What are your thoughts on today's video? Share your views with us in the comments below. Also, don't forget to give this video a thumbs up, subscribe to the channel, and ring the bell icon for more amazing videos about space. And thank you for watching.